In the boundless cosmos, are we alone? From H. D 85,512b to Kepler for 5 to B. Distant worlds have ignited human imagination. They are not merely scientific discoveries, but represent our eternal quest for another Earth. Today, let us draw closer to these potentially habitable exoplanets, lift their mysterious veils, and explore the possibility of life in the universe. This video will take you deep into potentially habitable exoplanets for humanity. In the boundless cosmic theater, each newly discovered exoplanet is like a lone lamp suddenly lit, drawing our curious and yearning gaze. Among these distant points of light, one planet named H. D 85,512b has, with its unique charm, stirred continuous ripples in the astronomical community and public imagination alike. It is not merely a cold celestial coordinate, but a giant question mark, a philosophical proposition prompting us to re-examine our own place in the universe. For science communicators, its story perfectly blends rigorous scientific discovery with captivating unsolved mysteries, making it an ideal vehicle to convey cosmic wonders to the public. The exploration journey of this planet is both a testament to human technological progress and a constant challenge to the limits of our cognition. The discovery of H. D 85,512b stems from humanity's relentless pursuit of technology. It was captured in 2011 by the high-accuracy radial velocity planet searcher HARPS at the European Southern Observatory in Chile using the classic radial velocity method. This method doesn't directly photograph the planet, but infers the planet's existence indirectly by precisely measuring the tiny wobble of the star caused by the gravitational tug of the planet. The amplitude of this wobble is extremely small, equivalent to detecting the speed change of a person walking slowly 1,000 kilometers away. The technical requirements for this are astounding. This planet orbits a K-dwarf star named H. D 85,512, about 36 light-years away from us. This distance is considered a neighbor on the cosmic scale, but under the understanding of our current technology, it remains an unbridgeable chasm, keeping us humble before any fantasy of reaching it. Every such discovery quietly speaks of the brilliance and limitations of human intelligence. What initially excited the scientific community was that H. D 85,512b was initially judged to be located at the edge of its star's habitable zone. The so-called habitable zone refers to a theoretical region around a star where the planetary surface temperature can allow liquid water to exist stably. As we know, water is the indispensable cornerstone of life on Earth. H. D 85,512b has a mass about 3.6 times that of Earth. Classified as a super-Earth, it orbits on a relatively close orbit, with an orbital period of about 58 days. However, its parent star H. D 85,512 is an orange dwarf star that is cooler and dimmer than the Sun. Therefore, even though it's close, the energy the planet receives is similar to what Earth receives from the Sun. This provides a theoretical possibility for the existence of liquid water. This discovery instantly set it apart from numerous exoplanets, propelling it to the top of the candidate list for the most potentially habitable exoplanets at the time, triggering widespread global media coverage. However, the charm of science lies in its constant self-correction and deepening with subsequent, more in-depth research and modeling analysis. The initial optimism was gradually replaced by a more nuanced, complex picture. A question emerged: does having liquid water equate to being habitable? HD 85512b provides us with an excellent starting point for discussion. Its larger mass means its surface gravity could be about twice that of Earth. What impact would such an environment have on potential life forms, skeletal structure, blood circulation? Even metabolic methods might need to be completely redesigned. More importantly, subsequent research indicates it is likely a tidally locked planet. This means one side will always face the star in perpetual daylight and scorching heat, while the other side always faces away, plunged into endless darkness and severe cold. Under such an extreme model, how could life survive? Perhaps only in that narrow twilight zone at the day-night boundary could relatively temperate conditions exist. But whether this environment is stable enough to nurture and sustain life is a huge unknown. These complex factors replaced the initial simple joy with deeper reflection. This leads to a deeper discussion. Is our definition of habitability too Earth-centric? We are always looking for another Earth, using the temperature, water, and atmospheric composition familiar to us as a ruler to measure everything. But could the forms of life far exceed our imagination? Perhaps on the perpetual day side of HD 85512b, there exist strange creatures relying on stellar light energy rather than chemical energy. Perhaps on its perpetual night side, organisms thrive in the darkness, relying on geothermal energy. HD 85512b forces us to think. Where exactly are the limits of life? Are we looking for a new home we can immigrate to? Or are we looking for any form of cosmic companion? No matter how strange, this topic is highly open and attractive, capable of igniting the audience's limitless imagination and discussion, and also filling scientific research with humanistic care and philosophical speculation. Another key point is the atmosphere, whether a planet is habitable. The atmosphere plays a crucial role. It is like a blanket able to regulate temperature, create a greenhouse effect, and block harmful radiation. Astronomers speculate through modeling that if HD 85512b is to maintain a suitable temperature, its atmosphere might need to consist of relatively high carbon dioxide concentration and at least 50% cloud cover. These cloud layers could reflect a significant amount of stellar light back into space, preventing the planet from overheating. But this remains a hypothesis to this day. We do not yet have the capability to directly detect its atmospheric composition. This involves the cutting-edge field of modern astronomy, how to study the atmospheres of distant planets. Next-generation space telescopes, like the now-launched James Webb Space Telescope, have one of their core missions being to analyze the spectrum produced when starlight passes through a planet's atmosphere as it transits its star, to discern molecular signatures within it, such as water vapor, carbon dioxide, methane, even oxygen. The atmospheric detection of HD 85512b will be a major test of our technology and theory. Its results may directly decide whether it remains on the list of hopes or is crossed off from it. This process is itself an exciting scientific adventure. Furthermore, we cannot ignore the influence of its parent star, HD 85512, as an orange dwarf star, has a lifespan far longer than the Sun's, and is relatively stable in activity. This provides life on the planet with a stable evolution time of tens of billions of years, even longer than the current age of the universe. This is an extremely enticing factor. But what about the star's early activity history? Did it experience frequent and intense flare eruptions, using powerful stellar winds to strip away the planet's primordial atmosphere? These factors make the habitability of HD 85512b a multidimensional, complex puzzle, not something a simple yes or no can answer. Every star has its unique character and history, which profoundly affect the fate of its planetary family. When we withdraw our gaze from HD 85512b itself and look towards the broader cosmic picture, its significance becomes more profound. Its discovery and ongoing research are a microcosm of human exoplanet science, transitioning from the age of discovery to the age of characterization. We are no longer satisfied with merely knowing a planet exists. We crave to understand their nature, their composition, their climate, their history. HD 85512b is a signpost on this long road of exploration. It tells us that the universe is filled with Earths of various models, some larger, some smaller, some hotter, some colder. They collectively enrich our understanding of planetary diversity and make us cherish Earth, this seemingly ordinary yet extremely special planet, even more. Ultimately, the story of HD 85512b transcends the scientific data itself, touching the root of the human spirit of exploration. It represents our deepest inner desire to seek answers and establish connection to the broader existence. Whether it is ultimately confirmed to be a hot desert world or a wondrous planet with unique life, its value will not be extinguished. It reminds us that the universe is a place full of possibilities. Every new discovery is both an answer and the starting point for 10 new questions for us on Earth. Studying distant worlds like HD 85512b is perhaps ultimately to better understand our own home, the fragility, uniqueness, and preciousness of Earth. While gazing at the stars, we also reflect on how to protect this blue ark, carrying all known life in the vast cosmos. And this process is precisely the most exciting part of scientific exploration. It connects humanity's past, present, and future, illuminating our long journey into deep space. Every gaze at a distant world is a deepening of self-awareness. This is the eternal charm of cosmic exploration. A celestial body about 1,400 light-years from Earth quietly came into human view. It was not fabricated by science fiction writers, but a real exoplanet discovered in 2015 by NASA's Kepler Space Telescope, Kepler for 5 to be. When its name first spread across the globe through news, It almost ignited the collective imagination of all humanity. Had we found Earth to point zero, another home suitable for human habitation, this discovery was not just a triumph of astronomy. It was a mirror reflecting humanity's most profound yearning, curiosity, and anxiety about its own destiny. Viewed from a professional astrophysical perspective, Kepler 450b indeed possesses a series of exciting habitable parameters. It orbits a G-type main sequence star, very similar to our Sun, Kepler 452. This star in size, temperature, and brightness is strikingly close to our Sun, just slightly older, about 6 billion years old, 1.5 billion years older than the Sun. Kepler 450b has an orbital period of 385 days, so close to Earth's 365 days. This means it lies precisely within the habitable zones, Goldilocks region of its stellar system. The so-called habitable zone refers to the region where the planet's distance from the star is just right, allowing surface temperatures to maintain stable existence of liquid water. And water is the most critical cornerstone for the emergence of life on Earth, based on the amount of stellar radiation it receives and its orbital characteristics. Scientists used the transit method to calculate its radius as about 1.6 times that of Earth, classifying it as a super-Earth. These data pieces together initially sketched a captivating picture highly similar to Earth's environment, like a long-lost twin brother waving to us from the depths of the universe. However, the rigor of science requires us to traverse the fog of excitement and face those huge unknowns and controversies directly. The first core point of controversy is it really a rocky, metallic planet like Earth? The Kepler telescope discovered it via the transit method. This method infers the existence, size, and orbital period of planets by precisely measuring the periodic dimming of a star's brightness, but it cannot directly tell us the planet's mass and composition. According to planetary formation models, a celestial body with a radius 1.6 times that of Earth could very well be a mini-Neptune-like gaseous planet with a thick atmosphere composed of hydrogen and helium, beneath which might be a high-temperature, high-pressure icy or liquid mantle, with no solid surface to stand on. If this were the case, then any discussion about surface liquid water or surface life would be meaningless, although many statistical models and comparative studies tend to favor it being more likely a rocky planet. This remains a reasonable, unproven scientific hypothesis to this day, requiring future, more powerful observation equipment to verify. Even if we optimistically assume it has solid land and a metallic core, a second severe challenge immediately emerges. What kind of atmosphere would it have whether a planet is truly habitable? The atmosphere is a crucial temperature regulator and life shield. Earth's nitrogen-oxygen atmosphere and moderate greenhouse effect create a pleasant climate, but Kepler 450b, due to its greater mass and stronger surface gravity, likely possesses a much denser atmosphere than Earth's. This could lead to two extreme consequences: either a runaway greenhouse effect, making its surface temperature like Venus's, reaching hundreds of degrees Celsius, enough to melt lead, or its atmospheric composition is simply unsuitable for Earth-type life to breathe. For example, rich in hydrogen or lacking key gas components, we do not yet possess the technical means to directly analyze its atmospheric composition in detail. This key piece of the puzzle is still missing. Next-generation space telescopes might be able to perform more refined transmission spectroscopy analysis, detecting the chemical fingerprints left when its atmosphere filters starlight each time it passes in front of its star. But this remains an extremely arduous task. This leads to the third, perhaps most thought-provoking discussion topic. Even if Kepler 450b has a temperate environment with vast oceans and continents, what would life there look like? We are always accustomed to using Earth life as a blueprint, to search for extraterrestrial life, looking for water, looking for so-called biosignatures like oxygen and methane. But could the creativity and diversity of the universe utterly surpass our imagination? Life there might be silicon-based rather than carbon-based, might breathe sulfide or nitrogen, enjoying biological chemical processes completely different from ours, or even exist in forms entirely beyond our comprehension. Is the other Earth we desperately search for fundamentally a cognitive limitation, restricting our broad understanding of life itself? Kepler 450b is perhaps silently challenging our human-centric view of life and the universe, forcing us to think about the potentially unimaginably strange diversity of life in the cosmos. Facing these exciting yet elusive unknowns, the most direct way is to go and see for ourselves. But this brings the most despairing reality check. The 1,400 light-year astronomical distance lying between. This is a physical chasm that humanity currently and in the foreseeable future can almost never cross using the fastest spacecraft ever launched by humanity, like the Parker Solar Probe, with its peak speed of nearly 100 kilometers per second, reaching Kepler 450b. would take over 20 million years. This timescale far exceeds the entire history of human civilization. It utterly negates the possibility of our generation, or even countless future generations, visiting it directly. For exploration, this cruel reality forces our exploration strategy to shift completely from traditional interstellar travel to interstellar remote observation. All our hopes are bent on the next generation, and the generation after that of space telescopes. For example, follow-up projects more powerful than the James Webb Space Telescope envision concepts like the Habitable Exoplanet Imaging Observatory. These future giant eyes might attempt to directly capture a faint point of light from this planet and, through extremely precise spectroscopic analysis, dissect its atmospheric composition, searching for biosignatures like oxygen or methane that might be produced by a biological activity. But we must clearly recognize that when we interpret these spectral signals, we will still carry the bias of Earth life. More importantly, the scene we see is what it looked like 1,400 years ago, because light takes that long to travel to Earth. We are not observing in real time, but interpreting a fossil light record from the distant past. From the cosmic Middle Ages, Earth was in China's Ming Dynasty at that time. Therefore, the deepest significance of exploring Kepler 450b actually far surpasses finding a backup home or another habitat. It is more a profound, philosophical, and scientific self-reflection. It acts like a cosmic-level philosophical question generator, constantly questioning humanity's true place in the universe. Are we a lonely accident, or an inevitability under universal laws of life? If the former, what kind of responsibility and meaning does this ultimate loneliness bestow upon human civilization? If not, how would the discovery of one or even multiple extraterrestrial neighbors fundamentally reshape our civilization, our religions, our technology, and even our self-perception? It simultaneously acts as a catalyst for an unprecedented technological revolution. To see farther and clearer, it continuously pushes the fields of aerospace engineering, optical technology, precision instruments, computer science, and data analysis to break through one limit after another. This technological spillover effect brought by exploration will ultimately benefit all aspects of human society. Perhaps the most precious gift Kepler 450b gives humanity is precisely its eternal sense of distance. It is like a bright mirror hanging in the depths of the cosmos, allowing us to reflect upon ourselves, to re-examine this currently only confirmed, fragile, and precious blue home, Earth. The grand process of searching for Earth to point zero precisely makes us recognize more clearly and deeply the uniqueness and the irreplaceability of Earth 1.0. It makes us understand that protecting the only land beneath our feet for the foreseeable future and gazing at the stars, exploring the unknown, are never opposing choices, but the two sides of the same coin of human wisdom and responsibility. So the next time you look up at the deep starry sky, imagining Kepler 450b, this distant and vague world in your mind, don't feel the slightest frustration or loss because of its unattainability. Its existence is itself the most generous gift given to us by the universe, an inexhaustible source of scientific inspiration, an eternal driving force propelling us to constantly question, explore, and transcend the boundaries of our own cognition. It quietly reminds us that the greatest journey of human civilization is not only a potential physical flight across vast light years someday in the future, but also in the present, our every inquiry based on curiosity, our every expansion of the knowledge boundary, our every profound reflection on our place in the cosmos. All these expeditions of thought began with our every pure, initial curious glance at the vast sea of stars, and Kepler 450b will serve as an important coordinate in this great gaze, continuously guiding our thoughts towards the deeper universe. On the deep curtain of the boundless universe, from time to time, a star becomes especially dazzling due to human perception. It is no longer just a navigator's coordinate or a poet's inspiration, but a place that may hold the answer to the ultimate question of whether we are alone. In recent years, one such star has stood out from the multitude of exoplanets. It is LHS 1140b, a world that makes astronomers' hearts race and sets all stargazers' imaginations soaring. It is not another Earth, but it might be the closest concept to another home we have discovered so far, and the debates and explorations surrounding it are dramatically reshaping our understanding of the universe and life. The discovery of LHS 1140b itself is a superb display of human technical wisdom. It is not directly visible. Astronomers captured traces of its existence through two exquisite indirect methods. First, the transit method. When a planet passes in front of its parent star, it blocks a tiny fraction of the starlight, causing a periodic and an extremely slight decrease in the star's brightness. It's like a giant, unseen hand in the cosmos holding an invisible marble, periodically passing in front of a distant lighthouse. Second, the radial velocity method. The planet's gravity causes the star to wobble slightly. By measuring the tiny changes in the star's spectrum due to the Doppler effect, the planet's mass can be inferred. It is through the combination of these two methods that we have been able to outline the basic portrait of LHS 1140b. It is a super-Earth, mass about 6.5 times that of Earth, diameter about 1.7 times, orbiting its parent star every 24.7 days. However, the true extraordinary part of LHS 1140b lies in its special location, the habitable zone. This region is vividly called the Goldilocks zone, meaning the planet's distance from the star is just right, making its surface temperature neither hellish like Venus nor frozen like Mars, thus allowing the key ingredient for life, liquid water, to exist stably. LHS 1140b's parent star, LHS 1140, is a quiet red dwarf, although dimmer and cooler than the Sun. Precisely because of this, its habitable zone is very close to the star. This raises a key question: wouldn't such a close distance cause the planet to be tidally locked, just like the Moon always shows one face to Earth? LHS 1140b likely also always shows one face to its Sun, one side in perpetual dusk, the other in endless night. This sounds like a dead end, but the latest research has proposed a disruptive idea. This might not be a disadvantage, but its greatest advantage for nurturing life. This is one of the most captivating current scientific discussions surrounding LHS 1140b. The traditional tidal locking model predicts one side as a scorching sea of lava, the other a frozen wasteland. Life seems to have no place, but computer simulations offer a more optimistic picture. If the planet possesses a sufficiently thick atmosphere, it could effectively transport heat from the perpetual day side to the perpetual night side, thus creating broad, temperate conditions suitable for liquid water and even life. And the twilight zone at the day-night boundary, that region of eternal dawn and dusk. Imagine a planet without sunrise or sunset, yet possessing an eternal spring, within a band-like region encircling the globe. This land might be forever bathed in the soft, red, sunset-like glow, its landscape fantastical, surpassing the imagination of any science fiction writer. Therefore, the presence and composition of LHS 1140b's atmosphere becomes the core of all questions and the focus of all debate. Finding the atmosphere is the prelude to finding life. For this, humanity has deployed its most powerful eye in space, the James Webb Space Telescope JWST. Its mission is to capture the spectrum produced when starlight passes through LHS 1140b's potentially existing atmosphere. As it transits its star, various molecules in the atmosphere will, like fingerprints, absorb light of specific wavelengths, leaving unique imprints on the spectrum. We are looking for water vapor, oxygen, methane, carbon dioxide, these so-called biosignature gases, especially non-equilibrium combinations, hinting at biological activity like photosynthesis or metabolism on Earth. Some early analysis data reported in 2023 once caused excitement in the scientific community, hinting that its atmosphere might be rich in nitrogen and even show signs of carbon dioxide, but this is far from conclusive. Data interpretation is full of challenges and uncertainties. The faintness of the signals, the influence of stellar activity itself, all require scientists to exercise extreme caution. Every observation clears a layer of fog, but deeper fog might lie ahead waiting to be traversed. This leads to another profound topic. Even if we really detect a combination like oxygen and methane, could we then announce the discovery of extraterrestrial life? The answer is likely no. This is where scientific rigor and philosophical speculation meet. Oxygen can be produced by non-biological processes. For instance, stellar radiation breaking down water molecules. We must rule out all non-biological possibilities before tilting the balance towards life. This process requires countless cross-validations and support from multiple lines of evidence. LHS 1140b thus becomes a perfect testing ground. It not only tests our technical limits, but also tests how we define life, how we interpret evidence, and how to responsibly announce a discovery that could rewrite human history under global scrutiny. Premature assertions only undermine the credibility of science, while excessive conservatism might make us miss the opportunity for understanding. Besides the mystery of life, the peculiar physical properties of LHS 1140b itself is also full of discussion value. Its high density suggests it might be a planet extremely rich in iron. Like an enlarged Mercury core, this means it might possess a strong global magnetic field. A magnetic field is an invisible shield for a planet's life, able to deflect deadly charged particle winds emitted by the star. Especially active red dwarfs often erupt with intense flares. If LHS 1140b indeed possesses this shield, then its ability to protect its surface environment and potential life would be greatly enhanced. On the other hand, its large mass also means its surface gravity could be about 1.5 to 2 times that of Earth. In such a world, what would the life forms that evolve look like? Plants might be lower and sturdier. Animals might possess tougher skeletal structures to cope with the strong gravity. All these speculations provide immensely rich material for us to think about the diversity and adaptability of life. When we gaze at LHS 1140b, we are not just observing a rocky planet 40 light-years away. We are conducting a thought experiment about humanity's own future. It makes us reflect on Earth's preciousness and fragility, and also ignites our ambition to cross interstellar space. Although with current technology, crossing the 40 light-year chasm would take tens of thousands of years, just as humans a few centuries ago could not imagine today's aerospace achievements. Who can predict the technology centuries from now? Perhaps one day, probes we send or our descendants themselves will truly set foot on that land of eternal twilight. Then, all our debates, explorations, and expectations today will become the prologue to that great chapter when we point our telescopes towards a faint red dwarf star about 22.7 light-years from Earth. We seem to have found a heart-pounding answer, Gliese 667 cc. This exoplanet, discovered in 2011, was once hailed as the strongest contender for Earth to point zero, even portrayed by some media as the most suitable new home for human relocation. But is it really as wonderful as we imagine? Gliese 667 cc orbits a star named Gliese 667c, and its stellar system is actually a rare triple star system. Imagine if 3 suns appeared in your sky. What a spectacular sight that would be. But don't be scared by the chaotic world and the 3-body problem. The situation in the Gliese 667c system is different. The other 2 stars, Gliese 667a and b, are K-type dwarfs forming a close binary pair, while Gliese 667c orbits them at a greater distance. From the perspective of Gliese 667cc, its host star Gliese 667c occupies an important position in the sky, while the other 2 stars might appear as bright as Venus we see, or even like 2 small suns, providing additional illumination, but not causing planetary orbital instability. This peculiar celestial spectacle is highly attractive in itself, making us ponder the diversity of planetary environments in the universe. What truly determines the fate of Gliese 667cc? Is its sun, Gliese 667c. It is an M1.5- type red dwarf star with only 1/3 the mass of the Sun, and brightness less than 1.4% of the Sun's. This means the planet must be very close to it to receive enough heat to maintain temperatures where liquid water could exist. Gliese 667cc is exactly that. It completes an orbit in just 28.15 Earth days. Its orbital radius about 0.1 to 5 astronomical units. This distance is much closer than Mercury's distance from the Sun. Such proximity brings a key issue. This planet is likely tidally locked. The concept of tidal locking is crucial for our understanding of exoplanet habitability. This means one side of Gliese 667cc will always face the star in the endless scorching daylight, while the other side always faces away, plunge into the eternal frigid darkness. In such an extreme environment, how could life survive? Scientists have proposed an interesting possibility. At the day-night boundary, there might exist a temperate twilight line. This could be an ideal zone for the existence of liquid water and the proliferation of life. However, the environment here is by no means heaven. It would be a world of eternal twilight. Atmospheric circulation might become the dominant force here. Hot air heated by the star constantly rises. Cold air from the dark side constantly sinks, forming superstorms sweeping across the globe. Never ceasing, such circulation patterns, while possibly aiding heat distribution, also create extreme weather conditions. The second severe challenge comes from the wild nature of its seemingly gentle sun. Please don't be deceived by the seemingly gentle and harmless name of red dwarfs. These most common types of stars in the universe are actually famous tyrants, especially in their youth. Red dwarfs often erupt with extremely intense flares. Their strength can be hundreds, even thousands of times that of solar flares. Each eruption means a large amount of high-energy X-rays and ultraviolet radiation will pour onto Gliese 667c's surface, enough to strip away the planet's atmosphere and expose the surface to deadly radiation. Even if the planet initially had a thick atmosphere and a global magnetic field to protect itself, under billions of years of continuous bombardment, could its atmosphere remain intact as its surface become a completely sterilized wasteland? This is something we cannot directly see from 20.7 light years away. Yet it is a crucial question from the perpetual day side of Gliese 667cc. Life forms resistant to high temperatures and radiation might evolve. These organisms might possess biochemical structures completely different from Earth's, might use different solvents instead of water, or have more efficient DNA repair mechanisms. On the perpetual night side, if a global ocean exists, geothermal activity could provide energy, nurturing ecosystems completely independent of sunlight, just like hydrothermal vents in Earth's deep sea, where life is sustained by chemosynthesis rather than photosynthesis. Even more excitingly, in the twilight zone, a transitional ecosystem might exist, where organisms could adapt to constantly changing light and temperature conditions, developing unique survival strategies. Are we looking for a home suitable for human immigration, or are we looking for signs of any form of life in the universe? These two goals seem similar, but are actually worlds apart. Gliese 667cc might be hell for humans, but for another form of life, it could be a perfect home evolved over billions of years. This thinking leads to deeper philosophical questions. What is the essence of life? Must it follow the pattern of Earth life? If the life form we discover bears no resemblance to Earth life, could we even recognize it as life? Is our search. Wearing a pair of human-centric tinted glasses from the start, discussing further, even if the environment of Gliese 667cc were miraculously mild, the 20.7 light-year space distance also constitutes an almost insurmountable distance of life. The light speed limit is the ultimate shackle set for us by the universe. At the speed of humanity's current fastest spacecraft, getting there would take over 300,000 years. This time span far exceeds the history of human civilization, even if we develop theoretically feasible nuclear fusion-powered spacecraft, increasing speed to 10% of light speed. A round trip would still take nearly 500 years, not even considering the time spent at the destination. Such timescales pose fundamental challenges to human lifespan and organizational forms. So, what is the meaning of investing such immense passion and resources to study these distant worlds? The answer perhaps lies in knowing ourselves. Studying Gliese 667cc, studying all exoplanets. Their greatest value is not in finding a backup Earth, but in helping us understand Earth's true position in the universe. It is a mirror allowing us to see through it, our own uniqueness and fragility. Analyzing its habitability is actually refining our understanding of the conditions for life's origin and sustenance. Every newly discovered exoplanet, whether a super-Earth like Gliese 667 cc or a gas giant like Jupiter, enriches our cosmic map of life. They tell us that planetary diversity exceeds imagination, and the possible forms of life might be the same. This process is itself the most magnificent exploration of cosmic mysteries by human intelligence from a technical perspective. Studying Gliese 667 cc has also driven huge advances in observation technology. To study such distant and faint celestial objects, astronomers developed radial velocity methods, transit methods, and various other detection techniques. Studying the atmospheric composition of these planets requires unprecedented spectroscopic analysis precision, directly promoting the development of next-generation space telescopes like the James Webb Space Telescope and planned projects like the Habitable Exoplanet Observatory HABEX and the Large Ultraviolet Optical Infrared Surveyor LAVOIR. These technologies are not only used to search for alien life, but also, in turn, help us better understand Earth's climate system and atmospheric evolution. Returning to Gliese 667 cc itself, it might ultimately prove to be a windswept, radiation-permeated barren world, never able to become a new home for humanity. But this will not diminish its importance in the slightest. As an early discovered super-Earth within the habitable zone, it has forever changed astronomy. It inspired us to build more powerful telescopes, developed more refined models. It made us dare to imagine that rocky planet suitable for life in the Milky Way and even the universe might not be exceptions, but common. It is estimated that in our Milky Way alone, there could be tens of billions of planets located within the habitable zone, and Gliese 667 cc is just the beginning of this vast treasure trove. The story of Gliese 667 cc also reminds us that scientific exploration is a process of constant self-correction. The initial excitement and the Earth to point zero image and media reports may become more complex and nuanced. With more data and deeper analysis, this is not a failure of science. This is precisely the power of science. It is willing to adjust or even abandon previous views based on new evidence, gradually approaching the truth. This ability for self-correction is the biggest difference between science and dogma. Ultimately, the search for exoplanets like Gliese 667 cc is essentially our tiny civilization's great attempt to answer the eternal questions in the vast starry expanse. Who are we? Where do we come from? Where are we going? Touching the farthest corners of the cosmos in 2010, an exoplanet named Gliese 581 grams burst into astronomers' view, instantly igniting global enthusiasm. It was not a blurry point of light in a telescope, but a tangible possibility, a shocking conjecture about another Earth, about extraterrestrial life, even about humanity's future home as a planet orbiting the red dwarf Gliese 581. It lies precisely within its star's habitable zone, where temperatures are suitable, theoretically allowing for liquid water to exist. And water is the source of life as we know it. The discovery of this new planet was not only a technical victory, but also a philosophical inquiry, forcing us to re-examine our own place in the universe. The discovery process of Gliese 581 grams is itself a legend of scientific dedication and wisdom. It was captured by a team led by Stephen Vogt of UC Santa Cruz and Paul Butler of the Carnegie Institution for Science, using the renowned Keck Observatory's spectrometers via the radial velocity method. This method doesn't directly image the planet, but infers the planet's existence by precisely measuring the tiny wobble of the star caused by the planet's gravitational pull. Gliese 581g's gravitational tug on its star is extremely weak, causing the star's radial velocity to change by only a few meters per second, equivalent to a person's jogging speed. To filter out such a signal from decades of hundreds of such precise data points is like discerning the sound of a pin dropping in a noisy stadium. This achievement demonstrates the astonishing precision human technology can reach, and hints that Gliese 581 grams might be a rocky planet with a mass about 3 to 4 times that of Earth, a truly super-Earth. However, the path of science is never smooth. Shortly after Vogt's team announced this exciting discovery, another top team, researchers from the Geneva Observatory in Switzerland, reanalyzed their data, but failed to confirm the signal of Gliese 581 grams. They believed the signal might be noise from the star's own activity, like spots and flares, misinterpreted during complex data processing. This doubt immediately pushed Gliese 581 grams from the most promising habitable planet into a fog of controversy. This scientific debate is crucial. It is not a simple dispute of egos, but a perfect embodiment of science's self-correcting mechanism. It reminds us that, before the ultimate answer is revealed, maintaining cautious optimism is necessary. It is also this rigorous questioning that drives the emergence of subsequent, more powerful telescopes and more advanced analysis methods, seeking to finally solve this mystery. Even if Gliese 581 grams is confirmed to exist, living on such a world would be a fantastical sight, drastically different from our earthly experience. Its host star is an M-type red dwarf, much smaller, dimmer, and cooler than the Sun. Therefore, to receive enough heat to maintain liquid water, Gliese 581 grams must orbit very close to the star. Its orbital period might be only just over 30 Earth days. This means its year is less than 1.5 of our months. Such proximity leads to an inevitable consequence: tidal locking. Just as the moon always shows one face to Earth, Gliese 581 grams also likely always shows one face to its sun. The other side plunge into eternal darkness. Thus, this planet is extremely divided into two, one side in perpetual scorching daylight, the other in perpetual severe cold and dark night. This sounds like a cruel world incapable of nurturing life, but hope lies precisely at the boundary of light and dark, the twilight line, in this narrow band-like region encircling the planet. A scene of eternal dusk or dawn might exist. Here, light and temperature might be relatively mild, becoming an ideal refuge where liquid water can persist and even life can proliferate. Imagine residents there might never see sunrise or sunset. Their entire world is an endless belt of shifting twilight colors. The background, a huge, dim, red sun in the sky. What strange creatures and ecosystems would evolve in such an environment? This provides immensely broad imagination space for us to think about the diversity and resilience of life. Red dwarfs are the most common long-lived stars in the universe. Habitable planets discovered around them have thus become primary targets in the search for extraterrestrial life. But beneath the gentle exterior of red dwarfs lies a bad temper. They are usually extremely unstable in their youth, frequently erupting with intense flares and deadly ultraviolet and X-ray radiation. This high-energy radiation is enough to strip away a planet's atmosphere and sterilize any nascent life budding on its surface. Therefore, whether Gliese 581 grams can be truly habitable depends on a core question. Does it possess a sufficiently strong Earth-like global magnetic field? This magnetic field would become a shield guarding life, deflecting the deadly stellar wind, protecting the atmosphere and surface water bodies. If it lacks this shield, then even located in the habitable zone, it might just be a barren, dry rock ball. This leads to a deeper discussion. Must life necessarily require conditions like Earth's? Our search has always used Earth as a blueprint, following the template of liquid water, suitable temperature, atmosphere. This is, of course, reasonable, as it's the only sample we know. But is this a kind of Earth-centric limitation? Perhaps the forms of life in the universe far exceed our imagination. They might not need water, but use ammonia or methane as solvents, might not breathe oxygen, but rely on other chemical processes, or might not even exist on planetary surfaces at all, but lie hidden in subsurface oceans. The extreme environment of Gliese 581 grams is precisely the best case to challenge our inherent thinking. Broadening the definition of life, it forces us to think. Where exactly are the limits of life? Are we looking for another Earth, or are we looking for life itself? Even if Gliese 581 grams is ultimately proven not to exist, or its environment is too harsh to inhabit, its scientific value and cultural significance will not fade at all. Its discovery and the ensuing controversy greatly advanced the science of exoplanets. It brought concepts like the habitable zone and tidal locking into the public eye, inspiring countless people's interest in astronomy. Returning to the initial question, is Gliese 581 grams hope or illusion? For now, it is both. It is a beautiful, unresolved question at the scientific frontier, a scientific hypothesis waiting to be confirmed or refuted. But its true value has long transcended its physical existence itself. It represents humanity's relentless spirit of exploration. Represents our purest curiosity about the unknown. It reminds us that the universe's greatest mysteries are waiting for us to uncover. And every time we look up at the starry sky, we are casting a greeting glance towards countless possible worlds, searching for Gliese 581 grams and thousands upon thousands of planets like it. In the end, is us humans seeking our own coordinates and companions in the sea of stars. This great adventure has only just begun. The American Kepler Space Telescope, launched in 2009, like a keen ear extended by humanity into deep space, diligently listen to the subtle pulses between stars, searching for those distant points of light, dimming almost imperceptibly as planets pass by. It was within this ocean of data that in 2014 a world-designated Kepler 186f leapt into scientists' view, instantly igniting the infinite imagination of the global astronomy community and the public. It was dubbed Earth's cousin by many. But beneath this dazzling halo, what kind of real world is it truly? What is the significance of humanity crossing light-year barriers to explore it? And what revelations does it bring for our pressing future on Earth? To debate the discovery of Kepler 186f was a glorious victory for the transit method. This exoplanet hunting technique, scientists calculated the basic parameters of this planet by precisely measuring the periodic slight decrease in brightness of its parent star, Kepler 186. It is located in the constellation Cygnus, about 500 light-years from Earth. Its size is about 1.1 times that of Earth. One of the first exoplanets discovered within the habitable zone. With a size extremely close to Earth's, this habitable zone is sometimes poetically called the Goldilocks zone, referring to the region where the planet's distance from the star is just right. Here, temperature conditions theoretically allow liquid water to exist stably on the planet's surface. This is widely considered one of the most critical elements for the emergence and continuation of life. However, being located in the habitable zone does not necessarily mean it is livable. The real environment of this planet may far exceed our wildest imagination, or perhaps be cruelly disappointing. Its parent star, Kepler 186, is an M-type red dwarf star, smaller, cooler, and more volatile than our Sun. This means that to receive enough heat to reach suitable temperatures, Kepler 186f must orbit very close to the star. Data shows its year is only equivalent to 130 Earth days. Such proximity triggers a series of severe challenges. First, it is likely tidally locked, just as the Moon always shows the same face to Earth. Kepler 186f might also have one side in perpetual twilight, daylight, the other side in the endless, bitterly cold, dark night. Only near that narrow and elongated twilight circle might relatively mild areas exist. This extreme climate pattern is drastically different from Earth's balanced day-night cycle. Secondly, M-type red dwarf stars are notorious for frequent and intense flare eruptions, continuously bombarding their close-orbiting planets with high-energy X-rays and ultraviolet radiation. This intense stellar wind might have long ago stripped away the planet's fragile atmosphere. Without an atmosphere of sufficient thickness and suitable composition, the planetary surface cannot maintain liquid water nor shield against deadly radiation, and temperature regulation is impossible. Therefore, whether Kepler 186f still retains an atmosphere and what its atmospheric composition is, these are core questions for judging its true habitability. But with our current technology, precisely detect its atmospheric spectrum across 500 light-years remains an insurmountable challenge. This leads to a profound discussion topic. Is our obsessive search for another Earth unintentionally limited by our own Earth-centrism? We always use Earth as a blueprint, searching for those planets with rocky surfaces, liquid water, and suitable temperatures. But must the forms of life necessarily be so? Astrobiology proposes more open possibilities. Perhaps on the perpetual night side of Kepler 186f, beneath ice caps, ecosystems exist that rely on geothermal energy rather than sunlight. Perhaps its life forms don't need water at all, but are based on liquid methane or ammonia, or perhaps life has long existed in a form of pure energy or chemistry we completely cannot understand. Is our definition of habitability too narrow? The value of Kepler 186f might not lie in whether it is like Earth, but in how it, as a completely different world, challenges and expands our entire understanding of life's possibilities. Even if Kepler 186f itself is not a paradise for life, its discovery holds milestone significance. It proved that in the Milky Way, rocky planets similar in size to Earth are not rare items, but common. The Kepler 186 system itself has 5 planets. Kepler 186f is the outermost one. Its existence strongly hints that the universe is filled with countless Earths waiting to be discovered. They vary in size, environments diverse, collectively constituting a grand planetary spectrum. This greatly increases the probability of us finding companions in the universe, also changing our position and self-perception in the cosmos from a lonely special case to an ordinary member of the cosmic planetary family. So, is it possible for us to truly touch this world, the 500 light-year distance, with current or even foreseeable future technology? Is a despairing chasm, human-launched spacecraft like Voyager 1 would take tens of thousands of years just to exit the solar system's edge, let alone cross hundreds of light-years of interstellar space. Currently, our exploration is limited to remote sensing, using increasingly powerful telescopes like the James Webb Space Telescope to analyze its atmospheric composition, searching for biosignatures like oxygen, methane, water vapor that might be produced by biological activity. This is like standing on one mountain peak, observing the outline and haze of another distant mountain with a telescope, trying to infer the types of flowers at its foot. This indirect detection method is full of uncertainty and interpretive space. Therefore, another issue worth deep reflection emerges in an era unable to reach in person. What is the meaning of investing massive resources to explore these distant planets? Is it to satisfy humanity's innate curiosity? Is it to find a future refuge, or is it to more profoundly understand our own home? The answer is likely the latter. Studying exoplanets like Kepler 186f is actually a mirror for examining Earth by constructing its climate models, simulating how it evolved under different conditions. We can, on the contrary, grasp more accurately the operating mechanisms of Earth's climate system by contemplating how a planet's habitability is lost or maintained. We can better appreciate the preciousness and fragility of Earth's environment. This research, in a sense, is a giant cross-space-time comparative experiment. What it ultimately teaches us is how to better protect humanity's current only, irreplaceable home as for the dream of interstellar colonization. In the case of Kepler 186f, it should be viewed more rationally. The idea of treating it as a backup Earth or escape pod seems overly naive and dangerous, scientifically and ethically. Scientifically, terraforming an environment that's vastly different, potentially already possessing native life world, the required technology and capability far exceed humanity's current level. Ethically, do we have the right to appear as a potential invasive species, disrupting a balance another world may have taken billions of years to evolve? If we recklessly modify it just because it's unsuitable for us, how is that fundamentally different from the destructive behavior towards our own Earth home? Kepler 186f should more be an object for us to contemplate our own responsibilities, not a target for us to plunder. Humanity's future lies first in solving crises on Earth, not in pinning hopes on a distant and illusory arc. Looking back at Kepler 186f, it hangs in the deep darkness 500 light-years away, a blurry yet enticing pixel. It is both a challenge to our technical capabilities and an invitation to our imagination. It might be a dead, barren rock, or it might be hosting miracles of life we cannot understand. Whatever the truth, its discovery has already directed humanity's gaze further, forcing us to ponder some of the most fundamental questions. Are we alone in the universe? How universal are the laws of life? How should we treat the world we possess? For everyone who looks up at the stars, the very existence of Kepler 186f is a huge encouragement. It reminds us that the universe is still full of unknowns and possibilities. The footsteps of exploration should never cease, and ultimately this great interstellar exploration journey will ultimately lead us to understand ourselves more deeply, and with moral and humility turn back to cherish and protect this blue planet, brimming with life under the sunlight, our only one, Earth. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries, and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.